AMD is reinventing its chiplet architecture from the ground up. New silicon, new packaging, and a new layout that is so different you can see it with your naked eye. And the best part is, we don't have to speculate anymore, because there's a chip out there that already has a little bit of Zen 6 DNA inside. In this video, we will analyze AMD's next-gen chiplet architecture in detail. We will talk about changes to the silicon, explore the new packaging technology behind it, and uncover a major implication for the next generation of 3D V-Cache. And of course, we will talk about Strix Halo, the chip that is a test run for AMD's future. Right now, I'm holding AMD's future in my hands. And I mean that literally, because the ROG Flow C13 I'm holding and recording with is powered by Strix Halo, a chip that's already using AMD's next-gen chiplet architecture. Strix Halo is quite literally a glimpse into the future. But what exactly makes Strix Halo so special? And what does it tell us about the next generation of Zen CPUs? Let's find out. Just by looking at it, we can see that Strix Halo is different. It looks nothing like AMD's current chiplet design, which hasn't changed since the introduction of Zen 2 back in 2019. AMD's original chiplet architecture was so good it not only paved the way for AMD's return to success, but even AMD's latest Ryzen 9000 CPUs still use the same technology. Zen 2, 3, 4 and 5 look so much alike because they are based on the same fundamental chiplet design. But not Strix Halo. It's not a monolithic chip, but almost looks like one, visually much closer to Intel's tile-based designs like Arrow Lake and Lunar Lake. But that's just what we can see on the surface. What about when we look inside the silicon? Lucky for us, ASUS Tony and Colonel over on Twitter created some amazingly detailed die shots which allow us to literally take a peek inside of Strix Halo. And lucky for me, because that means I didn't have to sacrifice the Strix Halo inside the ROG Flow C13 that ASUS sent me. I honestly was close to take it apart for die shots, which would have been a shame because this tablet-sized computer crushes my desktop PC in video editing. Strix Halo consists of 3 dies, all manufactured in TSMC's N4P process node, 2 CPU chiplets called CCDs, and a SoC die. With dimensions of 16 by 19.2 mm, the Strix Halo SoC die is about 307 square millimeters in size, more than 2.5 times the size of a Ryzen 9000 I/O die with only 120 square millimeters. When we look at the silicon, we can see that Strix Halo has a massive memory system. Left and right at the borders of the chip, we can spot 4 32-bit low-power DDR5X memory PHYs each. That's a total of 8 PHYs for a combined 256-bit interface. The memory controllers are directly next to the physical layer and handle all the input and output commands. There's one controller for every 32-bit PHY, and right next to the controllers, we can spot the 32 megabytes large MAL cache, which stands for Memory Attached Last Level, also called Infinity Cache. It's split into 8 clusters of 4 megabytes each with corresponding memory tags. 4 clusters on the left and 4 on the right. It's all symmetrical. Each side contains 4 memory PHYs, 4 memory controllers, and 4 MAL clusters with 4 megabytes each. There's a lot of 4s in Strix Halo. Just for context, a single side contains what can be considered a modern high-end memory system. And Strix Halo has 2, literally double the memory bandwidth of most competing APUs. And there's only one reason for this massive memory system. It's the even larger integrated GPU in the center of the chip. AMD basically built a discrete graphics engine into the SoC die, which in my opinion should be called graphics die instead. The iGPU has a total of 20 RDNA 3.5 workgroups divided into 2 rows of 10. And since a single workgroup contains 2 compute units, there's a total of 40 compute units in Strix Halo. If that doesn't tell you much, it's more than a RX 7600 XT, which has 32 compute units. We are talking about GPU power previously only found in dedicated GPUs. This amount of compute units in an APU is unheard of. And it explains why Strix Halo has such a wide memory interface. Because such a massive GPU requires a lot of bandwidth. We are literally looking at an upper middle class GPU disguised as a mobile APU. It's also a full-fledged RDNA 3.5 implementation with hardware ray tracing. The GPU in Strix Halo is so strong, I can comfortably play Helldivers 2 at medium to high settings with over 60 FPS on a tablet-sized system. That's the performance you get with a mobile RTX 4060 or even 4070. Above the workgroups, we can find the rest engines, the local GPU cache, and other MISC areas. And in the middle, I would locate command, control, and interconnect functions. Strix Halo also has a pretty beefy neural processing unit located below the memory system on the left side of the chip, with 32 Exynos cores based on Xilinx technology AMD acquired a while ago. Below the right side memory system, we can find 2 media engines and the display engine. And at the bottom of the chip, we can locate 16 PCI Express 4.0 lanes plus USB 2, USB 3, and USB 4. But we haven't talked about the most interesting part yet. In the beginning of the video, I said that Strix Halo contains a little bit of Zen 6 DNA. At the very top of the SoC die, we can see 2 strange-looking rectangular areas which are filled with a large amount of what looks like tiny interconnects, not unlike the TSV contact points we discovered in the Zen 5 chip deep dive. To figure out what that is, we have to look at the entire chip, including the CPU chiclets. Once we zoom out to include the 2 CCDs, which contain the Zen 5 CPU cores, we can see that they are directly attached to the area of the SoC die we just talked about. And when we look inside the CCD itself, we can see that they contain the very same structures. What you are looking at right now is AMD's next-gen die-to-die interconnect. This is the Zen 6 DNA I was talking about, right there in plain sight on Strix Halo. Now that we know what AMD's new interconnect looks like in silicon, let's try to understand how it functions. And for that, we have to understand how the previous generation works. When we compare a Granit-rich CCD, that's the chip used for the Zen 5-based Ryzen 9000 desktop CPUs, with a Strix Halo CCD, we can clearly see similarities and differences. The Zen 5 CPU core complex, including the 32MB shared L3 cache in the center, is unchanged. It's the same exact cores and the same number of cores, but the area below it is very different. There is some power management and chiplet control logic that has been moved around to fit the new interconnect, but what we are really interested in is how the interconnect area looks like. On the desktop Zen 5 CCD, we can see a row of larger logic blocks. We can even count them, there are 18. And on the Strix Halo CCD, we can see multiple rows of tiny interconnects, a very striking difference. And there's also a size difference, albeit a small one. The Granit-rich CCD is almost 70 square millimeters in die size, while the Strix Halo CCD is slightly smaller at around 67 square millimeters. Strix Halo is using different silicon which required a new tape-out. But how did these two visually very different interconnects work? The row of 18 logic blocks on the Granit-rich CCD are so-called SerDes, which is short for serializer, deserializer. And like so many things in semiconductors, they actually do what the name implies. SerDes take a signal and either serialize or deserialize it. Let me explain. Modern chips are massive and complex machines that work with many parallel signals. A Zen 5 CCD has a huge internal signal network. If you want to connect the CCD to an I/O die, you can't just route all the internal signals from the CCD to the I/O die. That would literally take hundreds and hundreds of interconnects. That's where the SerDes come in. They take the parallel signals from the CCD, transform them into a serial signal, and then send this serial signal over a high-speed interconnect, which is literally a copper wire on the substrate, to the I/O die. The I/O die has a corresponding set of SerDes which receive the signal and deserialize it again. And it works the same way when the I/O die sends data to the CCD. The Infinity Fabric on-package interconnect that AMD has used since Zen 2 is a serial interconnect. CCDs and I/O die use SerDes to transform the signals from parallel to serial and back again in order to communicate with each other. SerDes are used in almost all communication that transitions the boundaries of a single chip. It's for example how PCI Express works. When your GPU wants to communicate with your CPU, the PCI Express SerDes on your GPU create a serial signal that is routed from the PCI Express slot to your motherboard and then to your CPU, which has the same kind of SerDes as your GPU to receive the signal and decode it again. With a SerDes, you can transform complex parallel signals into simple serial signals that can be sent via just a few high-speed wires over long distances. And PCI Express is a great example because the Infinity Fabric SerDes that AMD introduced with Zen 2 and still uses for Zen 5 are based on the SerDes design of PCI Express. SerDes are part of what we call the physical layer of PHY. It's the part of a semiconductor that translates the digital data into real-world signals like electrical pulses. That's what I mean when I call something a PHY. We are literally talking about the physical implementation of an interconnect. But there's another part to an interconnect, the data protocol that determines what, when, and how data is transmitted. The best way to explain it is to think of a highway and cars traveling on it. The highway would be the physical layer, meaning the SerDes and the wires that connect them. It literally exists in hardware. And the cars traveling on that highway are the data protocol. You can use different cars on the same highway, which means you can run different protocols on the same physical interconnect. Or you can use the same car on different highways, which means you can run the same protocol over different physical interconnects. When you design an interconnect, you have to design a physical implementation, how you actually connect the individual chiplets, and you have to create a protocol which controls how the data is handled. AMD's Infinity Fabric on package is using SerDes, which are related to PCI Express, and then runs the Infinity Fabric protocol on them. If you think of Infinity Fabric as a kind of PCI Express for chiplets, you are not that far off. But there's one more interesting fact about the Infinity Fabric on Ryzen CPUs. Remember that we counted a total of 18 logic blocks on the Granit rich CCD? That's because a CCD actually has two independent Infinity Fabric links. Each link consists of an 8-wide serial interconnect and a so-called parity bit. And since 8 plus 1 is 9, each Infinity Fabric link has a total of 9 logic blocks. And because there are two links, we can count 18 blocks in total. AMD also calls these links GMI, which is short for Global Memory Interconnect. There are two variants of GMI. There's GMI-wide, which uses both links, and there's GMI-narrow, which, you guessed it, only uses a single link. Ryzen consumer CPUs only use the GMI-narrow implementation of Infinity Fabric on package, while GMI-wide is reserved for AMD's EPYC server CPUs, which means on Ryzen, one of the Infinity Fabric links on a CCD is always unused. The corresponding I/O die also only has 2 Infinity Fabric links in total, because even with 2 CCDs, like on a Ryzen 9 9950X, that's all AMD needs for GMI-narrow, which is also the reason why Ryzen CPUs with a single CCD have a slightly worse memory bandwidth than those with 2 CCDs, because a single CCD with only one GMI-narrow link is not enough to fully utilize the memory bandwidth that the I/O die can provide. We can actually calculate the maximum theoretical bandwidth of a CCD that uses GMI-narrow. All we have to do is count. Since one of the 9 logic blocks per link is a parity bit, it's an 8-wide interconnect. AMD's Infinity Fabric on package protocol supports 32 bytes read and 16 bytes write operations per cycle, which is the clock speed of the Infinity Fabric. At 1800 MHz, which corresponds to DDR4 3600 on an AM4 system, that's 57.6 GB per second of read and 28.8 GB per second of write bandwidth. And with 2 CCDs, you get double that. Running the ADA64 memory test on my single CCD Ryzen 5800X3D, which runs at 1800 MHz Infinity Fabric, confirms our calculations. While the memory read bandwidth isn't limited by the Infinity Fabric speed, the write bandwidth is literally capped at the 28.8 GB per second that a single GMI-narrow link offers. Increasing the Infinity Fabric clock speed also increases the bandwidth between the CCD and the I/O die. And because on Ryzen, the Infinity Fabric clock is tied to the memory clock, faster memory also results in a faster die-to-die interconnect. Now that we know how AMD's current Infinity Fabric on package interconnect works, let's take a look into the future. And that means Strix Halo. As we've seen, the Strix Halo CCD, internally called Goldtail, uses the same Zen 5 CPU cores as Granit Ridge, but has a different interconnect. What did AMD change and how does it work? With new process nodes, everything gets smaller. But one thing that is very hard to scale down in size are SerDes, which are a combination of a digital and an analog system. They don't really get that much smaller anymore, even with better process nodes. The multiple rows of tiny interconnects on Strix Halo can't be SerDes. They are way too small and there are way too many of them. So what are they? Remember how I said that you can't just connect 2 chiplets without using SerDes because you would literally need hundreds of wires? Well, I lied a little, because while it is much more complicated and highly complex, it is possible. And with Strix Halo, AMD is doing just that. AMD is switching to a so-called fan-out interconnect. But I really like the way AMD is describing it as a sea of wires, because that's what it actually is. The concept of a fan-out interconnect is simple. If you want to connect two chips with each other, the most forward way is to just use wires from one to the other. And if you don't want to use a serial connection with SerDes, you have to use a lot of wires in order to maximize the interconnect area, so you can use the greatest number of wires possible. The wires literally have to fan out from the chip, meaning they go beyond the boundaries of the die. Like an old school fan. That's where the name comes from. And because a modern fan-out interconnect requires so many wires that a simple 2D fan-out isn't enough, the fan-out isn't only happening on a planar space. The wires are spread out across multiple layers. But you can't just stack wires on top of wires. You have to build a structure around it to support such a complex system of multiple layers of fan-out interconnects. From what we know, it's almost certain that AMD is using TSMC's Info OS technology. Info is short for integrated fan-out and OS means on substrate. It's a form of advanced packaging that uses an interposer, but unlike TSMC's CoWoS or Intel's Foveros, it does not use a silicon interposer. Instead, it's based on a so-called redistribution layer, or RDL for short. An RDL is sometimes also called an organic interposer, as opposed to a silicon one. It consists of layers of copper, which transport the electrical signals, and layers of a polymer dielectric material compound to isolate the signals from each other. The chiplets, in the case of Strix Halo that means the SoC die and the two CCDs, literally sit on top of this organic interposer, which contains the hundreds of tiny interconnects from the CCD to the SoC die. AMD actually released images that show a top-down view of the RDL interconnects and a cross-section of the Strix Halo package. From the top-down view, we can see that there are multiple layers of RDL interconnects and how they fan out. There are so many wires stacked on top of each other, the image is getting very cluttered in the center. A very high interconnect density and something you could not achieve without an RDL. The cross-section image is even more interesting because it shows each layer of the entire package. The substrate on the very bottom is the greenish or sometimes bluish PCB that most CPUs sit on. It connects the CPU on top with the pads or pins on the back that fit into the motherboard socket. That's also where the current gen Infinity Fabric on Package interconnects are routed. Next up are the C4 bumps, which usually directly connect the substrate to the CPU. But with the new fan-out interconnect, there's one more layer, the organic RDL interposer. It sits between the C4 bumps and the chiplets. The chiplets itself are connected to the RDL via small silicon pads. The RDL is the area where the fan-out wires are routed, and we can see how much smaller they are compared to the interconnects inside the substrate. This miniaturization is what allows the higher interconnect density. The wires are literally smaller, which they have to be because you need hundreds of them. There are so many wires, in fact, that AMD can just continue the internal data fabric of the CCD over to the SoC die without transforming the signal. No SerDes are needed. It's almost like both dies are sharing the same silicon. So what are the advantages of this new fan-out die-to-die interconnect? The number one benefit isn't actually performance related, it's efficiency. Using SerDes and high-speed serial interconnects requires a lot of power. The data needs to be transformed from parallel into serial signals and vice versa. And because a serial interconnect can't transport a lot of data simultaneously, it has to make up for that with a high clock speed, which also uses a lot of energy. The Infinity Fabric on Package interconnect AMD introduced with Zen 2 consumes about 2 picojoules per bit. And while we don't have specific numbers for AMD's new design, it's most likely orders of magnitude more efficient. A fan-out interconnect requires much less energy to transport data between two chiplets. That's also why Strix Halo, a mobile APU, was the perfect chip for a test run, because energy efficiency matters most on mobile. The second major benefit of a fan-out interconnect is latency. SerDes not only use a lot of power, transforming the signal takes time, which adds latency. With a fan-out interconnect, which just continues the fabric from one die to the other, there's almost no latency penalty. It's a stateless interconnect that doesn't need to go to sleep to conserve power and doesn't need to wake up or switch power states. It just directly sends the data without any stops in between. The third aspect of an interconnect is bandwidth. And while a fan-out interconnect can offer a lot of bandwidth, it's actually not a major benefit because a SerDes-based interconnect also allows for very high bandwidth designs if you run it at a high frequency. AMD stated that the new interconnect supports 32 bytes of read and write operations per cycle. But of course we don't know how many interconnects AMD is using and what clock speed they run at. I've run some tests on my ROG Flow C13, and while it clearly shows much higher read, copy, and write bandwidth than even a 9950X, it's difficult to accurately test the new interconnect, something I'm sure TSMC is much better at. I actually got the highest write bandwidth at over 200 GB per second when I was running a game in the background, because then the memory system seems to run at full speed. But running a game at the same time as a memory benchmark is also poison for the read bandwidth and the latency. Still, we can clearly see that Strix Halo does offer a higher interconnect bandwidth. But there are also downsides to this new type of interconnect. First of all, it's a more complex implementation that requires an organic interposer and advanced packaging technology in order to build the microscopic interconnects. Using TSMC's InfoOS is certainly more expensive than the previous Infinity Fabric on package solution. And it's also less flexible from a layout point of view. With the old Infinity Fabric, AMD could basically place the chiplets wherever they wanted. The SerDes-based interconnect allows for longer distances between chiplets. With the new fan-out, the chiplets have to be placed right next to each other. The shorelines of a chip suddenly become a limited resource. And there's one more big question mark regarding AMD's 3D cache. With Zen 3 and Zen 4, AMD placed the X3D cache chiplets on top of the CCDs. But with the latest Zen 5 CPUs, such as the 9800X3D, the 3D cache was placed below the CCD, a solution that offers better thermal heat dissipation for the CPU cores. The new organic interposer changes everything. Routing hundreds of tiny fan-out interconnects through the RDL already adds a lot of complexity to the packaging, but routing them through a silicon-based 3D cache chiplet is something else entirely. It's not impossible, but in my opinion, highly unlikely. If AMD manages to combine the RDL fan-out interconnect with a cache chiplet below the CCD, I will be more than impressed. I think with Zen 6, we will see the 3D cache return to the top of the CCD, which wouldn't be without a bit of irony. Zen 2 was a massive success for AMD. It wasn't only a great CPU architecture, but jump-started AMD's transition to TSMC and introduced the now legendary Infinity Fabric on package interconnect. Without it, AMD wouldn't be where it is today. But it's time for something new. And with TSMC's integrated fan-out on substrate packaging technology, AMD has the perfect replacement. Fan-out greatly reduces the cost to transport data from one die to the other while reducing latency at the same time. Getting rid of a SerDes-based interconnect was only a matter of time. The benefits clearly outweigh the increase in packaging complexity and cost. A step the competition already made, which only shows how good the original Zen 2 design was, as it's still competitive in 2025. Mobile and server products will benefit the most from this new technology. Mobile because here every watt counts, and servers because the energy savings of multiple chiplets quickly adds up. On desktop, the main advantage will be the reduction in latency. Strix Halo is more than just a test run for AMD, it's a path into the future. And it's the perfect chip to demonstrate the benefits of the new interconnect. It honestly feels unreal to have so much power in such an efficient mobile APU. And I count myself lucky because ASUS sent me a ROG Flow C13 even though I'm not a review channel. My first idea was actually to take it apart and use it for die shots, but that quickly changed when I experienced how powerful it is. I knew that 16 Zen 5 cores would be faster than my 5800X3D, especially in video editing. But I didn't expect by how much. I've started using the ROG Flow C13 as my primary editing machine. This tiny tablet-sized PC is really outperforming my desktop, and because I can take it everywhere I go, I always have my main system with me, which seems like a dream, but Strix Halo and the new die-to-die interconnect make it possible. And that's what makes me excited about the future. Thank you to ASUS, and if you want to check out the ROG Flow C13, I've put a link in the video description. If you are looking for an actual review, there are plenty of great videos here on YouTube. I hope you found this video interesting, and see you in the next one.